configurable systems. Okay, yeah, such as the Linux kernel, yeah. So how do companies realize these variant systems? Developers use two contrasting strategies. They either use clone and own, in which they clone a variant and they modify it to create another variant. So consider the example of a basic calculator, which was cloned and modified to create a scientific calculator, which was then used to create a financial calculator. Now, this strategy is strongly favored by developers mainly because it is easy to adopt and it offers quick innovation. But of course, there are a few problems. Consider the scenario where there is a bug in one of the variants, and because of cloning, the bug is replicated in the other variants as well. Now, if a bug fix is executed, to be able to propagate the bug fix or synchronize the variants, developers have to manually perform clone detection, which is very error prone considering that there is no traceability between these clones. Additionally, clone and own offers difficult reuse. Consider that there is a new set of customer requirements. Now, without the notion of which features are implemented in a variant, it is difficult to establish which variant should be cloned to create another or the incoming variant. And as a result, developers have to manually perform feature location, which is error intensive and also error prone. Yeah, in addition. So alternatively, developers can use software product line engineering. In SPLE, there is a centralized platform in which every feature is implemented once. This platform is supplemented with a configurator tool which takes feature selections and generates corresponding variants. Now, SPLE offers better control as well as healthier reuse and maintenance than the clone and own approach. However, it also has a few drawbacks. It is expensive to apply and it requires developers to perform tasks that they are not familiar with. For example, incorporating variability or adding feature models or variability mechanisms, etc. Companies typically do not start with SPLE. They start with clone and own, and then they attempt to migrate from a set of lean variants to an SPL-based architecture. Now, this migration is, there are a few frameworks that propose how to approach this migration process, but these frameworks are mainly single step or they follow a big bang strategy, which renders them risky in practice. Additionally, these frameworks, they require developers to recover metadata that was never recorded in the first place, which is pertaining to the information of where are the clones that requires clone detection and what features are implemented in the clone. And this requires feature location. So both clone detection and feature location mainly rely on heuristics, which makes the process very error prone and it leads to inaccuracies in the migration process. And then developers also have to spend some effort in incorporating the variability. For example, adding if-defs or any other mechanism for adding variability. And the last thing is that most existing migration frameworks are restrictive in that they restrict the developers to use either clone and own or SPLE, but not switch between the two. The goal of our work is to find out how to bridge the gap between clone and own and a fully integrated platform in a smooth and accurate manner. Our idea is to exploit the spectrum between clone and own and SPLE by introducing different governance levels between the two to bridge the gap. So, to make the process smooth, we prescribe a truly incremental strategy, and to make it accurate, we rely on proactively stored metadata. Let's dive into it. So, first we would look into the governance levels which we use to bridge the gap. We start with clone and own, in which we have a lean set of variants. And then we have clone and own with provenance, in which we record the traceability between the clones automatically and silently in the background so that the developers don't have to perform any clone detection. Then we have clone and own with features. Now, here we urge the developers to add the information of what features are implemented in a variant. These features in a number of ways, for example, as comments as is seen in this example. And then the organization can just maintain a list of features that it supports. The benefit is that developers don't have to perform feature location for tasks such as bug fix, replication, or feature introduction or feature enhancement, etc. Next, we have clone and own with configuration. And in this, on top of the existing feature mappings, developers incorporate any variability mechanism, for example, if defs, which are a very common way. Now, the benefit is that developers can allow configuration. That is that they can provide feature selections and derive variants from the set of existing variants. Next, we have clone and own with a feature model in which developers perform an analysis between the relationship between the features and organize them in a tree-like structure. Now, the benefit is that the feature selections can be checked for validity against the feature model. And then last, we have integrated platform with clone and own, where the developers relying on the stored metadata combine or merge all the variants into a centralized platform. And once we have a centralized platform, then it's easier for the company to ensure consistency and quality in the variants, in the subsequent variants. Now, to provide that or to materialize that, we have our framework called the virtual platform. The virtual platform is a framework that generalizes different clone management and product line migration frameworks. It works on top of a few conceptual structures that are semi-structured representations of source code in memory. I will just explain them in a few seconds. On top of the conceptual structures, we have operators that offer dedicated support to move along the spectrum. I'm sorry, I'm hearing some noise. Can you mute? I'm getting distracted. Yeah. So yeah, the operators, they generally fall in the umbrella of asset-oriented operators and feature-oriented operators. And we store and exploit the metadata that otherwise gets lost, mainly pertaining to clone traceability and asset traceability. So first, let's look into the conceptual structures. We have asset, which is any artifact that belongs to a variant or a repository. Asset can be of any type, including a repository or a directory, or even a method or a block of code. Every asset in our virtual platform is an asset tree because it's hierarchical. And to make our framework language independent, every asset is also an abstract syntax tree. Assets are mapped to features, where feature is any set of functionality that is meaningful to a customer, for example, calling functionality in a phone system. Then we have a feature model, which is a tree-like structure of features. Now, in the virtual platform, asset of any type can have a feature model for flexibility. And then lastly, to store traceability between clones, we have a trace database that stores traces between assets or features and the clones of them. Now, for the operators, we have asset-oriented operators that reflect the traditional development activities, and they track the changes and manage the versions of the various assets in the asset tree. Let's assume that you have an asset tree. Now, the operators that are responsible for managing or manipulating this asset tree are add asset, remove asset, or change asset or move asset, the basic operations that developers perform in their day-to-day routine. So in the asset tree, you have a root node, a virtual node that is responsible for holding the different repositories or variants. It also has a special relevance in the versioning of the asset tree. The versioning of the asset tree starts with 1, the basic integer form. And then after every update in the asset tree, the global version or the version of the root node is incremented and assigned to the affected assets. Let's assume that you have this asset that was updated. This would lead to the global version being incremented and assigned to the affected asset. Now, continuing with the asset-oriented operators, we also have clone asset, which during cloning automatically stores a trace between the original asset and the clone in the trace database. Now, assume that you have this asset tree and you have to, the developers clone this from variant 1 to variant 2. Clone asset would automatically create a virtual asset in the asset tree, and it would also create a trace between the asset and its clone as the version of the asset at the time of the clone in the trace database. Now, this version becomes relevant in change propagation, which is done by propagate to asset. Propagate to asset, what it does is that it automatically propagates changes from a source to its clone. Let's assume that this asset, the cloned asset, is modified by the developers. Now, this leads to the global version being incremented and assigned to the affected asset. If the developers want to propagate this change to the clone, they would have to invoke propagate to asset. The propagate to asset would automatically traverse the trace database to find the trace at the space between the asset and the clone. It would automatically detect the changes made in the asset and propagate them to the clone, and also store a trace between the asset and its clone, marking the last version at which the asset was synchronized. So with this, we have the asset-oriented operators, but then we also have feature-oriented operators. There are a few basic ones for managing the feature model. For example, adding features, removing features, changing features, or moving features. Then we have add feature model to asset, which adds a feature model to an asset of any type. Consider that you have this asset tree and this feature model on the right side. Add feature model to asset, add this feature model to the asset. And now any feature from this feature model can be mapped to any asset in this asset tree. This is exactly what is done by the map asset to feature operator. Map asset to feature adds the feature to the presence condition of the asset that implements it. For example, you have this block of code that shows a method called sum, which is mapped to the add feature. Virtual platform would add this add feature to the presence condition of the sum method, and in this way, it would map the asset to the feature. Now, what are the benefits of the two kinds of metadata that we stored, the clone traceability and feature to asset traceability? Developers can query the system using a set of convenience operators that we provide. For example, to get the mapped assets of a feature, or to find the clones of an asset or a feature, or to automatically detect changes and propagate them. Developers can clone assets along with the features that they map to using the clone asset operator. And a novel use case of our framework is that developers can clone entire features along with the assets that implement them across repositories or across variants. And then lastly, relying on the stored metadata, developers can automatically propagate changes between assets or features to their clones without the need of expensive clone detection or feature location. So this concludes our framework's details. And then we move on to evaluation. So for the purpose of evaluation, we implemented a Scala-based prototype of our virtual platform, our framework. And then we chose a case study of Clapper Web Tools. And the development of this case study strongly relies on a lot of branching and forking and cloning between the variants. What we did was that we simulated the development of the branches, and then we retrofitted the virtual platform operators to the actual activities performed in the commit. For example, adding a file or removing a file, or adding a feature or removing a feature. And then we counted the number of invocations of each operator, which led to this table. Now, what we did was that we performed a cost and benefit analysis in terms of time. We had a few incurred costs, which were the added costs of adding features and feature mappings that were done by the developers, and the cost of fixing the mappings that the developers forgot to add. And then we have the saved costs, which are the costs of clone detection and feature location that the developers were able to bypass because of the stored metadata about clone traceability and feature to asset mappings. Now, the benefit is the difference between the saved cost and incurred cost. We assume, based on previous research, that the cost of locating one feature or the cost of locating one clone roughly takes 15 minutes. We also assume that the cost of fixing a forgotten mapping is 10 times the cost of adding it proactively. Based on our analysis, we reach a break-even point of 54 seconds, which means that if developers take 54 seconds to add one feature or one feature mapping, they reach a break-even point. In practice, however, the features or the information of which feature a developer is implementing is fresh in the developer's subconscious. And it takes little time to materialize that in the actual source code or artifacts. We do envision greater accuracy if the virtual platform is used alongside development, which is one of the future works. So to sum up, we provide a framework called the virtual platform, which bridges the gap between clone and own and SPLE by introducing different governance levels between the two. We provide a set of conceptual structures, and on top of those, a few operators. And then we evaluate our virtual platform on a real world case study of 4 variants, and our preliminary analysis shows promising results. And with this, I finish my presentation, and I would be happy to answer your questions.